In the last video, we looked at the basis of Hückel theory, and we derived an expression where if we just consider two atomic orbitals, we would have to solve this determinant in order to find the energy of our orbitals. In this video, we're going to look at aromaticity. Here I've written down how probably most people know Hückel theory when it comes to aromaticity. When a hydrocarbon has 4n plus 2 pi electrons, it's aromatic, whereas if it only has 4n pi electrons, it's anti-aromatic. We're going to look into what that means and where these rules come from. We will look at two examples, one of which is the cyclopropenyl cation, which looks like this. It has 2 pi electrons, and to make it a bit simpler, I will number the carbon atoms 1, 2, and 3. So if I want to write down the determinant for this system, I will need to check what atom or what carbon is bonded to which carbon. Carbon 1 is bonded to itself, so as we learned in the last video, we put an alpha minus E, and this is the same for each of the diagonal elements. And now we have to see carbon 1 is bonded to carbon 2 and carbon 3, so both this and this gets a beta. Carbon 2 is bonded to carbon 1 and 3, so again, for carbon 2, it's bonded to 1 and 3, so we put a beta here, and similarly for carbon 3. And this determinant is meant to be equal to 0. In order to find the energies, we need to solve this determinant, and I'll walk you through how to do this. First, we're going to add the bottom rows to the first one. If we do this, we get alpha plus 2 beta minus E, alpha plus 2 beta minus E, and alpha plus 2 beta minus E. Well, the next two rows stay unchanged, so beta, alpha minus E, beta, 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 alpha minus E. What this allows us to do is to factor out alpha plus 2 beta minus E, and we're left with alpha plus 2 beta minus E, a determinant that looks like this. Okay, next up, what we want to do is simplify the determinant a bit further, and an easy way to do it is to get rid of the ones which we find here. So we could, for example, take this here, this row or column, minus this column. So we do this, minus. If I do this, we get alpha plus 2 beta minus E. The first and the second column stay unchanged. And then we have 1 minus 1, 0. Beta minus beta is 0. Alpha minus E minus beta, so alpha minus beta minus E. What this achieved is that now we have two zeros in one of the columns, so we can expand across this column, which puts a factor of alpha minus beta minus E in front, and we're left with a 2 by 2 determinant. So I write down alpha plus 2 beta minus E, alpha minus beta minus E, and our 2 by 2 determinant is 1, 1, beta, alpha minus E, which we can now just expand by going 1 times alpha minus E minus beta times 1, so that we're left with alpha plus 2 beta minus E, alpha minus beta minus E, and alpha minus beta minus E equals 0. This way of solving the determinant allows us to immediately read off the solutions, because this product has to be 0, and the product will be 0 if each of these terms is 0. So if we look at this term, when is it 0? I'll call it E1. It's 0 if E is equal to alpha plus 2 beta. And similarly, for these two, we find that it's 0 if E is equal to alpha minus beta. And we also notice that this is the same energy. That means we have one degenerate solution. So with this, we know the energies and how many energy levels there are. So if I draw an energy level diagram, it will look like this. Alpha plus 2 beta, alpha minus beta. And since we have 2 pi electrons, I fill the lowest level. So what can we say? We have a closed shell species. It's stable, since only a bonding orbital is filled. And we can also say that 4n plus 2 equals 2, so that n is 0, and we have an aromatic species. And indeed, if we look at NMR data, we can see that the hydrogens on this molecule are de-shielded by a ring current, which confirms that it's aromatic. And we also note that the number of energies we got is 3, which is the same as the number of orbitals we involved, which is 3. So number of orbitals is number of energies. Okay, that's the first example I wanted to show. The second example is cyclobutadiene, which looks like this, where we have 4 pi electrons. And again, I will number my carbons. Now, if I write down the determinant, first I'll write alpha minus E on the diagonal, since I can always do this, as each carbon is always bond to itself, if that makes sense. Then I know that carbon 1 is bond to 2 and 4, but not to 3. So I'll put beta here as 0 here, because it's not bond to 3, and a beta here. I'll do the same with carbon 2. Carbon 2 is bond to 1 and 3, but not to 4. So I'll give a beta here, here, but not here. And I'll do the same for carbon 3 and carbon 4. And this is the determinant I need to solve. Now, the first step will be just the same as with the other determinant. We'll add everything to the first row. And to make the maths a bit shorter, I'll not only add everything to the first row, I'll also factor it out immediately. So I get alpha plus 2 beta minus E. And my remaining determinant is 1, 1, 1, 1. Beta, alpha minus E, beta 0, 0, beta, alpha minus E, beta, and beta 0, beta, alpha minus E. Now, the next step I could do is subtract this column, or rather subtract this column from this, because then the 1s cancel, the betas cancel, and the betas cancel. So if I do that, I get alpha plus 2 beta minus E, as always. And then my remaining determinant will be 1 beta 0 beta, 1 alpha minus E beta 0, and then I'll get 1 minus 1 0 beta minus beta 0 alpha minus E minus 0 is just alpha minus E, and beta minus beta is also 0, and then 1 0 beta alpha minus E. Now I have 3 zeros here, which means I can expand across here, which factors out alpha minus E, and alpha plus 2 beta minus E, alpha minus E, and a 3 by 3 determinant, which is 1 1 1 beta alpha minus E 0 and beta 0 alpha minus E. Now, in the next step, what I will do is I will subtract this one from this one so that the betas cancel. So let me write that down. Alpha plus 2 beta minus E, alpha minus E, and then 1 1 1 stays unchanged. The second row also stays unchanged. And then beta minus beta 0 0 minus alpha minus E is minus alpha minus E, and alpha minus E. Now, what I'll find is that in the last row, I can factor out alpha minus E again, which if I write it down, I get alpha plus 2 beta minus E, and then alpha minus E squared, and then the determinant looks like 1 1 1 beta alpha minus E 0 0 minus 1 1. So the next step will be to subtract the first row from the last row. If we do that, we eliminate this 1, which gives us a column with 2 zeros. Okay, I'll write it down. Alpha plus 2 beta minus E, alpha minus E squared, and then we're left with 1 1 1 beta alpha minus E 0, and then 0 minus 1 is minus 1 minus 1 minus 1 is minus 2, and this is 0. So that means we can expand across here, which gives us a factor of 1. So no factor essentially, and leaves us with a 2 by 2 determinant, which we can then expand in the normal way. So this times this minus this times this, and it will give us alpha minus 2 beta minus E. So the final result is alpha plus 2 beta minus E, alpha minus E squared, and alpha minus 2 beta minus E, all of which is equal to 0. So again, we can just read off the solutions. E1 is alpha plus 2 beta, E2 and 3 is just alpha, and E4 is alpha minus 2 beta. And we also see that now we used 4 orbitals, so we also get 4 solutions. If I draw an energy diagram now, it looks like this. Alpha plus 2 beta, alpha, alpha minus 2 beta, and we have 4 electrons, so I fill them in. And here I fill them in parallel according to Hund's rule. So what this means, if we have four electrons, so that 4n is 4n equals 1, so we are anti-aromatic, right? Now we have a degenerate ground state if the molecule were to be aromatic and hence have a delocalized pi system, we have a degenerate ground state. This degenerate ground state is prone to distortion, the Jahn-Teller distortion, which makes our square cyclobutadiene distort into a rectangle, which looks like this, which shifts the energy level diagram like this, where one of these levels got stabilized and the other destabilized, so that if we fill it, it would look like this, which would overall stabilize our system. So we see that if we have an anti-aromatic system with 4 n-pi electrons, the orbitals will only be partially filled, which makes it unstable to distortion, which overall lowers the energy of the system. That is the basis of anti-aromaticity. And now, what we can also see from this discussion, if we look at this picture compared to the square I drew here, and if we look at this picture, the triangle, and this picture I drew here, we see that, or if we generalize, we can draw every polyhedra that's symmetric. We can draw the energy diagram by putting one of the corners on the lower end and then just completing the shape, as I will show here, and then drawing energies at each of the corners. And this works for our cyclobutadiene, and this also works for our cyclopropanol cation, and it will also work, if we look here, it will also work for benzene. Where I've just drawn the hexagon with one of its corners pointing down, and then respecting the rest of the symmetry of the shape. And then I draw one energy level at each of the corner. And for benzene, we have 6 pi electrons, which we can fill in like this. And we see in benzene, we have no unpaired electrons. We fill only the bonding the bonding orbitals, which means benzene is aromatic and stable. So these rules I wrote down earlier, they're a natural consequence of the molecular orbital approach, because 2 electrons will always be necessary to fill the non-degenerate lowest energy orbital, and then there are 4 electrons necessary to fill each of the degenerate sets that follow. So if you only have 4 n electrons, that will inevitably lead to having a degenerate ground state with unpaired electrons, as we saw in cyclobutadiene. And that's the basis of aromaticity. And yeah, that's where the rule comes from.